So now let's say we are given a uniformly distributed load at half span of the cantilever beam. We are given a uniformly distributed load. We are going to be applying the same way that we have been doing it. So now let's take a look at this. Now our shearing force at A here, our shearing force at A will be equals to this unit load times the distance from A to A, which is still 0. So our shearing force here is equals to 0 kilonewton, which is minus 0 kilonewton. It's still 0 kilonewton. So now that is our shearing force at A. Now our shearing force at X here would be this load times the total span of this load, which is our shearing force at X here is equals to minus the load here times the distance, which is X, then our kilonewton, that is minus W times X. Then our shearing force at B here, since there is no other extra load that is added at this particular point here, our shearing force at B will be equals to, it will still be minus W times X because there is no extra load there. It will still be minus W times X kilonewton. That will be our shearing force. Now, if we move on to our bending moments, the bending moments at A, since there is no distance between A and A, W times 0 will still give us 0. So we have is equals to 0 kilonewton meter. That is our bending moment at A. But now our bending moment at B will be equals to. So based on the former video, our bending moment, the formula for our bending moment is given by minus W times X square over 2, which is the formula for our bending moment. We have our X here. So our bending moment here is minus W X square over 2 kilonewton meter. That is the unit. Then also our bending moment at B, yeah, that is where it gets a little bit tricky. So now this is our bending moment at X. Our bending moment at B now would be equals to, so at this point we are going to apply the method at which I said earlier. So now let's say that this is the beam here, we have the beam here, is the line. So now this load which is here before that got to this point is equals to the shearing force of this load is W times S, where S is the distance between here and here. But we also have another distance here. Let us name it A. So our distance here is A from here to here. Let's say our distance here is A. So now if we have our shearing force at Ws, that means I can easily assume that for me to be able to solve it better, I can easily assume that our shearing force can become a point load at the centroid of this. The centroid is at the center of a UDL. So at the centroid, which the half of this place, which is x over 2. So at this point here, where this place is x over 2, and this other place, which is here, is x over 2. This point here is where I can now put my point load, which is the shearing force. The shearing force at point X, which is minus W times X. That is where I can now put my point load here. So if I imagine that my point load can be here, we have our X over 2, we have divided it into 2. Then the remaining distance, which is here, which is like distance A, would be equals to our bending moment at this point here would be equal to this one times the entire distance from here to here. So our bending moment at point here, which is point B, our bending moment at point B would be equals to W times X. Let's now open another bracket for the distance, which is X over 2 plus the distance here. We can imagine it as point A. Let me just put it there. We have point A or point Y. Let's say this is Y. The distance between here and here is Y. So M plus Y. Let's say this is Y plus Y. So this is the formula for the bending moment at B. The bending moment at B is equals to minus Wx times x over 2 plus y. Now this is the formula. So now let us impute some real values in there. Let's say that our kilometer per our load here is 2. We have 2, then this place is 2, our total distance is 5. Let's say this is 5. So here will be 3. We have 2, 3, 5. Then we have our 2 kilonewton per meter run. So now let us see that this is what we are given right here. So if we are to find for our shearing force, if we are to find for our shearing force at point A here, our shearing force at point A will be equals to this 2 here, which is minus 2 times the distance from here to here, which is 0. It will eventually give us 0 kilonewton. And at x here, our shearing force at x will be equals to this load here times the distance from A to X, which is minus 2 times the distance from here to here is 2, that is times 2 here, which is equals to minus 4 kilonewton. And then our shearing force at B, since there is no extra load, our shearing force at B is still minus 2 times 2, but there is no extra load here, so it should still be minus 4 kilonewton. Then if we move on to our bending moment, the bending moment at that particular edge A is automatically 0 because there is no bending at all. Now the bending moment at B here, we apply our formula. The bending moment at B is equals to minus 2 times the distance, which is our shearing force that we got here, then the distance from the centroid to here, which is 2 here divided by 2. That is, if we divide this length, this distance here by 2, we are going to get it. So we have our answer as d is equals to 2 divided by 2, 1. Everything here is going to give us minus 4 kilonewton meter as our bending moment at B. But now our bending moment at X. Now our bending moment at B, at point B here, is going to be bending, this is X. Our bending moment at B would be equals to, now we have our minus 2 times 2, which is our normal shearing force. So I say that if we imagine that this become a point load at the center, that is at the center of this, so we are going to be having this distance here 2 divided by 2, that is the distance divided by 2 plus the extra distance remaining, which is plus 3. So if we add it together, we have minus 2 times 2, open bracket, 2 divided by 2, 1, plus 3, we have 4. We have 2 times 4, 8, 8 times 2, 16. It's equals to minus 16 kilonewton meter. So that is how it looks like. Now, if we are to draw the shearing force diagram, if we are to draw the shearing force diagram, first of all, we pick our neutral here, we pick our neutral. Now, at point A, shearing force at A is equals to 0. So, this is the point at A. The shearing force at X is equals to minus 4. And minus 4 can be somewhere like here. The shearing force at B is minus 4, which is still the same place. So, this is a straight line, and this is a 1-degree line. So, we have here as 4 kilonewton. We have here as 4 kilonewton. Everything is negative here. This is our shearing force diagram. Then also our bending moment diagram at A here is 0. So we have 0 here. Let's do our neutral line. We have 0 as our bending moment diagram. Then our bending moment at X is minus 4 kilonewton. So we have minus 4 at this point. So if we have minus 4 at this point, then our bending moment at B is minus 16. We say minus 16 is here. So now in this place, this UDL, the UDL that we have here, we are going to be having a parabolic motion for it. Then for the rest of here we are just going to be having a straight line, which is a 1 degree line. So we have here as our minus 4 kilonewton meter. Let's put it as 4 kilonewton meter. We have 16 kilonewton meter. Everything here is negative. So this is our bending moment diagram. Our bending moment diagram for this.